So I'm going to go ahead and get started. Well, thanks everybody for making it in with the rain and some aforementioned possible power issues with the rain. This month, um, welcome to the amateur uh, the Tucson Amateur Astronomy's Fundamentals Special Interest Group, otherwise known as AFSIG. I think most people are some regulars on this meeting. I don't think we have any new members, or at least new attendees.
I do.
Oh, hey, oh, John. Okay,
Don Williams, yeah.
cool. Welcome. So for the since those joining us for the first time, this is we try to do two presentations a month. One on a general astronomy topic, and another that for a while has been focused on an astronomer of the month. Running out of topics to present on those, so this month I'm redoing some older material while I figure out what to present on next. So this month, I'm going to start with a presentation on the constellation Pegasus. Uh, give some hopeful observing ideas when monsoon season finally breaks. And then following that up with representing a 2019 presentation I did on supernovas. So if you do have questions, you can feel free to interrupt me at any point, or you can type them into the chat. I do pay attention to that, and I will address them as they come up. And without going ahead and getting started with, can everyone see my screen also, by the way, before I can?
Yep.
Cool. So Pegasus is the seventh largest constellation in the night sky, just behind Hydra, Virgo, Ursa Major, and a few others. It is one of the original 48 constellations that was outlined by the Greek astronomer Ptolemy sometime in the 2nd century. But its origins go a little bit back a little bit farther, and was originally part of a Babylonian constellation, which basically just represented a big grain field in their terms. I chose this constellation to bring it up mostly because it is highest in the night sky from July to November. So it gets in a pretty good observing position by the time monsoon season breaks here in Arizona. Some notable things it contains: it has 4 open clusters, 1 globular cluster, and a slew of galaxies that are brighter than 12th magnitude. I normally limit the objects that I talk about in these presentations to 12th magnitude or brighter, mostly because anything like going closer to 13th magnitude generally requires really good skies or fairly large optics to make out reasonably. So I try to keep it towards targets that are within good visual range and not designed to be photographic targets. And for those of you who have seen some of these before, it's been a couple of years since about a year or two since we've done a constellation. It is Pegasus is one of the few constellations where the brightest star in the constellation is not give it the designation Alpha, which part of the Bayer designation system, where an astronomer labeled many of the brighter stars in every constellation with a Greek letter. But as the constellations changed over time, these got moved around some. One very notable deep sky object that's worth calling out, and we'll talk about at the very end of this presentation, is Pegasus is also where you can find the small galaxy group Stephan's Quintet, more recently brought to the spotlight by the James Webb Space Telescope as being one of the first science images that it released. So here is a quick star map of it here in the night sky. It is located almost not quite circumpolar, about the mid polar latitudes from here within Tucson, giving it really close to the zenith area of the night sky once it gets close to around midnight this time of year, giving it a really good observing position throughout most of the night. It's close to the Andromeda and the Andromeda Galaxy, and it's actually one of several. The Great Square here in Pegasus is actually one of the astrozones that helps make it easy to find where the Andromeda Galaxy is. So it's definitely one of those that's worth at least knowing some about. Like many of the original constellations, it does have a fair amount of Greek mythology or other lore associated to it. It has been traditionally depicted as a great white horse with wings, with feathered wings, and in Greek lore, it is the child of the Gorgon Medusa. During the hero Perseus's battle, when he decapitated Medusa, the blood from her head fell on the ground, and this is said to have somehow birthed Pegasus and one of his brothers. Not sure how that works with the Greeks, but they've done crazier things. One other interesting thing, it's kind of out of the way with him, but I thought it was kind of funny with overall lore, is apparently he at one point dug a spring somewhere in Greece that magically gave people who drank from it the ability to write better poetry, which is an odd superpower from a magic spring, but still quite quite funny for Greek standards. Sometime after that, he would be we transition over to the Greek hero Bellerophon, and he was off to go and kill the Chimera for one reason or another. We won't really get into Bellerophon's specific quest here. And the goddess Athena, looking to help him out, gave Bellerophon a golden bridle and told him to sleep in the temple of Athena. And there, Pegasus showed up one night, and Bellerophon then used the golden bridle to tame him. And they went on and did many adventures, and obviously helping Bellerophon slaying the Chimera was one of them. But he would go out through several other tasks, which we're really not going to get into because it was a great good time. But eventually, Bellerophon would coerce Pegasus into trying to fly to the top of Mount Olympus to go visit the gods. This, of course, was a big no-no, and the gods put a stop to that pretty quick. Couple of different ways. One was they said that they sent gadflies that caused Pegasus to buck Bellerophon off of him. Another telling says that Zeus sent some lightning or some mighty winds that caused Bellerophon to lose his balance and fall off Pegasus as well. Regardless, Bellerophon, for trying to climb to the top of Olympus, fell off Pegasus and died while Pegasus continued on, earning with his newfound freedom, and was given a stable at Mount Olympus and swore service to Zeus, where Zeus promptly turned him into a beast of burden and gave him the task of ferrying around Zeus, his entourage, or people he liked to show off to occasionally, and also his thunderbolts. Pegasus did a really good job at this, and as his retirement gift, Zeus granted him the honor of becoming a constellation in the night sky. So, for constellation stories and myth, especially in the Greek times, definitely not some of the stranger ones, especially when Zeus is involved. But still, this is moving on to things we can actually look at in the constellation now, is a brief list of some of the more notable objects. We can see from left to right We have some stars, some of the open clusters, uh, excuse me, the the globular cluster of SCA 15, which we'll talk about, and quite a large number of NGC galaxies that are brighter than 13th magnitude. Uh, excuse me. Unfortunately, when I was actually researching these, the open clusters really aren't that impressive compared to what we normally see with some of the more well-defined open clusters like the double cluster or some of the clusters you would see on the Messier catalog. Uh, in fact, if you go look at them on star charts or uh, digital planetarium software, they're really very hard to distinguish from the background star field. So definitely uh, not necessarily some of the best objects that you might want to go look at, but we'll touch on one of them, which is probably the more well-defined one. So starting off with some interesting stars to go look at, we'll start with Enif. This is designated Epsilon Pegasi, which is the Bayer designation. You'll like Alpha Centauri is another variation star with a Bayer designation. With just to give you an example, it is the brightest star in the constellation. It has an apparent magnitude of about 2.4. It is a slight but subtle variable star, so it's not always 2.4, but it's close enough for that. It is about 690 light years away, relatively close in the grand scheme of things. For context, the farthest star, the most distant star that we can see in the night sky, if you is the star Deneb, which is I think somewhere in like 1,700 to 1,900 light years away. So definitely in the mid range. It's definitely for stars that we can see in terms of distance. It is a very bright star, given its age and size, outputting about 8.5 to almost 10,000 times as much light as the sun does. But despite that luminosity, it is only about 7 times more massive. But it is about 190 times larger in diameter than our sun. So it is definitely one of those. Just from the radius, you can tell that it is a supergiant or entered the supergiant phase near the end of its life. And specifically, its spectral class is a K2, so it is a fairly hot K-class star. For those unfamiliar with the spectral class designation, the K is part of a color scale. The 2 is used to indicate temperature, with 0 being hottest on that particular letter grade and 9 being cooler. And the Roman numeral to the right of it, I, is used to designate the star's type, with I being a supergiant and V being a white dwarf. So it's just a quick read off of that. Given its mass, it will actually eventually transition into a white dwarf star and a planetary nebula, but there isn't really a timeline of when that would happen. So don't expect this on any human. Expect this to go supernova on any human timescales. Its name, excuse me, like many stars that we see in the night sky, still holds their original their Arabic names instead of Greek names. And Enif is Arabic for the word nose, which is fitting because Enif over here on the right in the constellation's asterism fits the nose, with these 2 bands being the back legs, the front legs, the neck, and the nose. So definitely a fitting name. Over here on the left is also a Hertzsprung-Russell diagram, which is basically just a fancy chart showing star distributions. And this is definitely a very cool and very large star in terms of where it would fit within the Hertzsprung-Russell diagram. So this here, this larger band here on the left, for those who need a refresher, this represents the main sequence line. Kind of up here is giants, and then up here are supergiants. So this is definitely one of the cooler and larger supergiants out there in terms of brightness. Well, so next up, we'll only do two more stars, and then we'll go on to some deep sky objects, which are my personal favorites. The next star is known as Markab, which is Alpha Pegasi. Despite the alpha designation, we said this isn't the brightest star. It's actually the third brightest star in the night sky, which is also unusual for an alpha. Usually it's either the brightest or the second brightest, depending on how they redrew the star charts in the early 1900s. Its magnitude is about 2.49. It actually just barely loses out on the brightness to the second brightest star, which is Sheet, which is magnitude 2.48. So I think that at some point it was more accurate measurements took Markab down from the second brightest to the third brightest star, or stellar evolution between Markab and Sheet made Sheet somewhat brighter, and so they had to, when they were updating this, Markab them got bumped down to third. It is actually a fairly close star, about 149 light years away for us, but it is relatively close to us in size. It is about only has a 2.25 times more massive than our sun, throwing off about 40 times more solar radiation. It has a spectral class of A0 or B9. So it's depending on which measurement and survey, they haven't quite settled on whether or not this star is a large B class main sequence star, or an entering into the giant phase. It might be somewhere in a transition point between those two in terms of its stellar evolution. So it is tentatively classified as a blue or white subgiant. And its name, not really other interesting things around this star, but its name derives from the Arabic word for horse saddle, which, there we go, which is relatively fitting because it sits right here at the base of the neck, right where a horse saddle would go. Okay, so with the Hertzsprung-Russell diagram here on the left giving us an idea of where it fits. So definitely on the larger size of main sequence stars, although not quite near the A or B territory. And then, actually, so that is the last star I'm going to do. One thing I do like about these two stars is their position and brightness makes them relatively useful for using them as stars for calibrating your go-to equipment. I use them a lot when I am doing my telescope alignment for those that have go-to systems. So definitely one of the two of those stars that I think it's worth knowing about just for that reason. Because of how long Pegasus is up, that they do get a consistent point of knowing those stars and knowing that you'll have them available to make your alignments a little bit less troublesome during the night when you're getting set up. Come on, next slide, please. What's going on here? Moving on to some deep sky objects that we can go look at that are in Pegasus. Well, the first one, and probably the one most people will go to with, depending on where they're at, is the globular cluster Messier 15. This is one of the larger globular clusters within our Milky Way galaxy. It has a magnitude of about 6.3, putting it just barely outside the range of visual. Depending on, if you're a little bit younger, you might be able to actually make out a faint fuzzy blob uh, of uh, this cluster with the naked eye in very rural, very dark skies. But definitely one of those that you could easily spot with a binocular when you know where it is. It is about 175 light years in diameter, and at the distance and uh, scale of this object, puts its apparent size to us is about 18 arc minutes, which is slightly larger than one half the size of the full moon. Just to put that into perspective. It is also one of the older globular clusters in our galaxy, clocking in at about 12.6 billion years old. Despite being on the Messier catalog, it was actually not originally discovered by Charles Messier. It was first found by French astronomer Jean-Dominique Maraldi in 1746, and subsequently added by Messier onto his catalog of things that he didn't want to go look at because they were not comets. Much to our benefit, though, it is a fairly good object to go look at, both visually and photographically, especially for those that do outreach activities within the group. It's definitely one of those I would put on my list of targets to go look at here in the fall for outreach. What some interesting things about this, which I did not know off the top of my head, is that it contains the first planetary nebula found within a globular cluster, which, for those unfamiliar with globular clusters, is a bit unique in and of itself. Most of the stars in a globular tend to be fairly old, as given by this age here, fairly stable. So finding a planetary nebula itself is a bit cool. Although I don't think it's one of those that you would be able to find with an amateur grade telescope. It will probably be one of those that requires a bit more of a professional or a photographic aid in order to locate. It also interestingly contains a double neutron star system, which not quite sure on the status of that, if it's one of those that's in stable orbit or perhaps one of those that in a couple million years may turn into a nova or a kilonova. But definitely one of the rarities of star systems with a double neutron star. To give you kind of an idea of what this might look like in your telescope, although a little bit embellished, this is a rough sizing of what the object would look like in an 8-inch Schmidt-Cassegrain using a 10 millimeter eyepiece. So definitely something to go look at. Fairly easy to make out with its brightness, and fairly well formed. So good under most seeing conditions. Excuse me. For those looking for it on a star chart. So as you kind of saw earlier, but more explicitly, if using ANIF, if you're looking at it for binoculars, if you can find ANIF, you can generally just search over and you'll easily spot M15 with binoculars without too much trouble. Next up on our list, we have the only globular cluster that I felt was worth talking about within the constellation, which is NGC 7193. It is a fairly sparse open cluster. As I kind of hinted at earlier, it's hard to distinguish from background stars except by some of their brightness. It's about 13 arc minutes in diameter from our perspective. Not really a reason to specify how wide it is in light years, because the stars are not actually gravitationally associated to each other from what we can tell. We haven't quite sorted that out yet, and I'm not quite sure Gaia data has given us some more information there. But it is about that should be 7,400 light years away. If there is a typo on that, I apologize. That's 7,400 light years. Like many of the NGC objects, it was cataloged by William Herschel. This one coming up on the end of his first round of catalogs that he assembled on in 1825. He started the NGC catalog in like the 1780s. So definitely one of the objects he added on very much later in his observational runs. And given its sparsity, it's definitely one of those. I'm on the fence about whether or not this would be considered a visual cluster or a photographic cluster, but you have a little bit of it here within this area and some of it down here. And so given the apparent magnitude of these stars, it might be a little bit difficult for without really good skies to make out the cluster itself from background stars. So it might be a little bit of a challenge for those who are looking at for something to go look at. This is a rough simulation of it, again, on an 8-inch Schmidt Cassegrain, but this one's using a 20 millimeter eyepiece because it is fairly spread out. And I'm not quite sure what star this is up here in the field of view. I'm going to have to go look at a much more detailed star chart to tell you. So it is fairly close to Enif as well, but more towards the body and underneath where would be his muzzle. So kind of in this area here. And for those interested, this Neptune and Saturn, this is accurate. This screenshot I updated last week. So if you're looking in that area, you'll also have Saturn to go look at, and Neptune as they're poaching that region of the sky. For the next big object to go look at is NGC 7331, sometimes designated as Caldwell 30. This is a fairly good photographic target as well. I actually have a picture of it, I believe, coming up from that I have taken just for a little bit of comparison. It is a fairly bright galaxy coming in at about magnitude 10.4. So definitely well within the range of 8 inches or larger, 8 inches or smaller on aperture size. It is about 40 million light years distance, and it's roughly the same size as the Milky Way, coming in at about 120,000 light years in diameter. Given its rough size, it was originally considered to be the same, that the Milky Way was originally considered to be a sibling, at least categorically, of Caldwell 30 here. But we, in the early 2000s, we eventually identified that the Milky Way is a barred spiral galaxy, and Caldwell 30 is an unbarred spiral. So a slight but subtle difference there, kind of negating that sibling relationship. One interesting thing about it is that this central bulge area, this bright spot here closer to the center, is actually rotating in the opposite direction than the rest of the galactic disk. Didn't really manage to find anything in my brief search about exactly what they think may have caused that opposite rotation to occur. But definitely one of those more interesting galaxy quirks that you occasionally read about. What's notable about this is the anchor galaxy of another galaxy group. These are, although not really seen here, these are actually background galaxies. But there are some other dimmer galaxies all around NGC 7331. So definitely, if you have really good aperture, like say a large Dob, for example, definitely something that you should go look at if you want to try to get the rest of the objects in this particular galaxy group. If you don't, it's still a very pretty object to go look at. Kind of giving you a rough size. This is showing apparent dimensions on again with an 8-inch Schmidt Cassegrain, but with a 10 millimeter eyepiece. So it's about roughly the size excuse me, of Messier 15. Definitely have a much brighter core, so definitely you'll be able to make out the core given its brightness. You'll probably need some good skies to make out anything farther past the midpoint on the galactic rim. Give you kind of an example. This was a rough image I took a while back of 7331. So you can see some of the fainter galaxies up here. This is only 1 hour's worth of data, but still decent enough. Needs a lot more work. So as to where this is within the constellation, it's actually closer near the bottom, near the front legs, following the one corner kind of over here. It's not quite sure which two stars are to help find out. I'd have to go look at it. I need to map this. Unfortunate thing about this particular star chart is it doesn't actually name the stars. I think this is Sheet. All right, I'm not mistaken. And lastly, the last object we'll talk about before we finish up this presentation is obviously definitely the more famous object that people who follow NASA's space telescopes will be familiar with is Stephan's quintet. This is a galaxy group. It is a fairly faint galaxy group for amateur standards, clocking in at magnitude 13 for the brightest galaxy in the cluster, and magnitude 14 and 15 for some of the others. The closest galaxy in this cluster is about 280 million light years distance. It was first cataloged by Eduardo Stefan in 1877, and its proximity makes it one of the most studied compact galaxy groups available to us in the night sky, which is also one of the reasons why James Webb had selected it for one of its first targets. Is there's just a lot of rich information that we can glean here. And current models suggest that of the 5 galaxies in the group, we'll only see 4 of them here from James Webb, that 4 of them will eventually merge. I don't think this one is part of the ones that will merge. So I think there's another one hiding back here as part of that. Despite its popularity from NASA images, it is most certainly a very difficult photo target to see visually. It is very, very small in terms of apparent size. So this is my typical 8-inch McCaster grade on a 10mm eyepiece. And since these are all magnitude 13 or dimmer, it will be like trying to hunt very, very faint fuzzy comets. So definitely, excuse me, definitely a challenge object if you're looking for that. Definitely really, really hard to go see. Definitely not worth it for photographers though, because they're just so small. But it's also conveniently located right next to the Deerlit group. So finding NGC 7331 gives you a pretty good waypoint to help try to orient yourself to finding Stephan's quintet if you are one of those that likes to do classic star hopping. And some quick references. Any questions or comments on Pegasus before we continue on? I'm not seeing anything coming up, so I'll assume that is a no. I hope that served as a good way to give you some ideas for fall to go look at. Definitely one of the main points. And moving on to the second half of our talk tonight, when I turn off. So this, get some water real quick. So continuing up from there and moving on to supernovas, which are definitely one of the more interesting things that we can unfortunately not really have much motivation in to go hunt for as amateurs, because very few of them are rarely bright enough that we can see them in our own equipment. Most supernovas are found through automated surveys, and definitely from galaxies much further away than we can reasonably get with our equipment. But occasionally some of them pop up. So we're going to touch on a little bit of the history of supernovas, what some of the more famous ones that were originally found, give a quick recap on star classifications and the evolution, how they eventually, how stars born and evolve, and then talk about three different categories of supernova and kind of what separates them apart from one another, and also some about what their uses are in modern astronomy. So supernovas, the term itself was coined by 16th century astronomer Tycho Brahe, who we've given a presentation on before, but Tycho, despite also having his name as a crater on the moon, was the teacher and mentor of Johannes Kepler, if I remember correctly, or a astute or a respected colleague, one of those two. He coined the term as after seeing what we'll talk about here is when he saw his first supernova, cataloging it as a new star, or in the Latin, which their papers were written at during the day, as a nova stella. Supernovas are one of several possible and exciting ways in which a star will ultimately end its life. There is some interesting exceptions. That particular star, IPTF 14HLS, is a bit of a weird one. We're not quite sure what happened with that. Definitely recommend Googling that one on your own time. But a little bit of a phantom star. The all supernovas are born when a very massive star, usually 10 times the mass or more of our sun, reaches the end of its life. There are occasional supernovas that will occur due to some other more interesting mechanisms, which we'll talk about briefly when we get to type 1 supernovas. They are critically important in terms of the evolution of the universe as a whole, and also extensively for life on Earth, because they are the sole source by which elements heavier than iron are created. So, all the gold, heavy metals that use in our computers, we all owe it to add some form or another to supernova or supernova remnants. They individually, a supernova will throw out enough light that they will outshine their parent galaxy, which, if for those of us who are fortunate to see the supernova last May in Messier 101, the Pinwheel Galaxy, will be able to appreciate exactly what that means. Definitely one of the closer supernovas we've seen within recent times. What distinguishes all supernova, though, from a scientific perspective, is looking at what elements are present or missing from their spectra when they are observed with professional telescopes. Excuse me. So just hammering a little bit here on the importance of supernovas. Many of these things past iron, which is here, iron 26, are all come from supernovas. I just showing this periodic. This chart is actually really cool when you delve into it a little bit more. But supernovas are responsible are one step on getting neutron stars and white dwarfs. So everything past iron at one point stepped through a supernova. So definitely a very important part of where we got to today. So in terms of ancient astronomy and the history of supernovas in general, the first one supernova that is identified in history records belongs to Chinese astronomers, where they cataloged the first supernova in the year 185 AD. This supernova was eventually chased back to an area between the constellations Centaurus and Circinus in 2006. So unfortunately, this particular stellar remnant is not part of the northern skies. It's definitely one of those you'll have to be in the southern hemisphere to go and hunt for. Which you might be wondering, well, if it's in the southern skies, how did Chinese astronomers find it, 2,000 years ago? The answer to that is what's known as precession, where the Earth's axial tilt has changed slightly throughout centuries. So at some point, this particular area of the night sky was much more visible to Chinese astronomers in the southern portion of China, which allowed them to identify it. The next supernova that was found was or cataloged occurred in the year 10,006, and it definitely is considered one of the brightest stars that was ever recorded. It comes from the constellation Lupus, which is a winter constellation here at the northern hemisphere. Its brightness was apparently at some point 1/4 that of the full moon. So about put it about as a minus 7.5. For context, for those that have seen Venus, Venus is typically at its brightest around a -4. So this would, I believe, have been easily visible in daylight when it exploded. We haven't quite identified the I don't well, we believe we found the remnant for it, but there's some debate about whether or not if it was a type, if its exact supernova type. Right now, it's leaning towards being a type 1A supernova. From there, we didn't actually have to wait much longer for our next one. With the next supernova that we could see from Earth was found in the year 1054. And this was the supernova that formed what we now know as the Crab Nebula, which is Messier 1 in the constellation Taurus. This is definitely a good object to go look at during the late fall and winter observing session. A little bit small, though. Recommend a little bit higher power to make it out in good conditions. When this star exploded, it was visible in daylight for about a week and brighter than Venus. So definitely probably somewhere around magnitude -5 or -6, since the current suggestion is the supernova 10,006 was about -7.5. Definitely saying that a lot tonight. Would have been a very interesting spectacle for people when they knew what possibly a sign of ill omen, given that this supernova was at the height of the Middle and Dark Ages. After that, we have to skip forward about 500 years to Tycho Brahe before we get to our next supernova. This supernova was found in the constellation Cassiopeia. And in 2008, we formally cataloged it as a type 1A supernova. We then have Johannes Kepler finding our next one after that, with this one being traced back to the constellation Ophiuchus by Walter Bade and Fritz Zwicky in the 1930s. It is the most recent supernova that occurred within the Milky Way itself, and was also cataloged as a type 1A supernova. So definitely one of those more common occurrent types of supernovas. And after that, the most recent significant supernova was the supernova of 1987, which drives most of its importance because it was the first supernova that was studied by modern imaging astronomers. However, this, despite its proximity, actually occurred in the Large Magellanic Cloud. So unfortunately, we wouldn't be able to see any part of it here in our northern hemisphere. So these are professional images from Hubble and other scopes. I need to pull up. No. There we go. Showing each of those 6 supernovas I just talked about, from left to right and top to bottom. Let me go. No, I don't want the pen. I want a laser pointer. So this is supernova, what we believe is the remnant as a Spitzer image of supernova 185. This is supernova 1006, supernova 1054, the Crab Nebula. Supernova, this is Tycho supernova with 1576, which was seen by the Chandra Space Telescope. This is supernova 1604, which is a mix of Hubble and Spitzer data. And lastly, we have supernova 1987A, which is a combination of Hubble, Spitzer, and ALMA data. Definitely some pretty cool objects, especially I haven't actually had a chance to observe 1576 or these earlier two. The Crab Nebula is usually one that most people might have been able to see if they've had their telescope during the winter session at some point, because it is a prominent dark sky object being on Messier's catalog. So you've talked about, a little bit about some of their history, not exactly what causes supernova to begin with. So when it comes to stars, there are 3 main figures that will be reported, namely the temperature of the star, at least its surface temperature, its mass, and its luminosity. And using any one of those 3 properties, you can, through simple physics and gas laws, help determine any of the other 2. And this allows us to find, just from those 3 basic properties, we can get a lot more other information about them, such as what the star's stellar class, its color, how old it is, which is important for telling us something about how that star is eventually going to die. From stars as they are born through nebula complexes, and they eventually transition to open clusters, and how the star dies is inevitably tied to how massive that star is. So using any of those 3 properties I just mentioned, we can work back to the mass, and it'll tell us something about how that star will evolve. So stars like our sun, which is a low mass star, will eventually transition into this white dwarf phase here. If we had a binary companion in our solar system, which we do not, the sun might have transitioned into a type 1a supernova, but we lack that secondary companion to have that effect. So our sun will eventually transition over here to a white dwarf. But for stars that are much more massive than our sun, 8 to 10 solar masses or more, they will go down this second route of exploding as a type 2 supernova and then winding up as either as a black hole or a neutron star. There's some other subtle variations about this. This is a very general overview. There's a lot of other uh, exceptions that can occur along this path in terms of how stars might evolve. But in general, this chart holds up pretty well. So from using those simple statistics, we classify all the stars with a specific letter, otherwise known as known through school from the mnemonic "Oh, be a fine girl, kiss me," is how many people might remember the stellar classes. With O being the largest and brightest stars, and M being the smallest and dimmest stars. And as I briefly mentioned during the presentation on Pegasus, we also add a number to this letter to denote what temperature the star is, with 0 being hottest and 9 being the coldest, and then a Roman numeral to help denote what phase of its life that star is in. And giving a better example of how that is, you have 1, 2, 3, 4, 5, 6, and 7 denoting various phases. So if you recall, Enif, which was the brightest star in Pegasus, was a K class, but it was a K, I believe it was a K2 or a K1. So to give you an example of just helping interpret that number a little bit more. And now we can finally talk about supernovas and actually what causes them. I had to lay down some work there. So type 1a supernova, and I need to double check something. Right. Sorry. I saw a message in the chat, but it was just a comment. So type 1a supernovas are more useful from a professional astronomer standpoint. These are notable in that we distinguish them because they do not have hydrogen in their spectra when we go and look at them with the spectrograph. They are further divided into type 1A, 1B, and 1C. Mostly what distinguishes these is a combination of spectra, a little bit more some physics in terms of how the actual star collapses. Don't let the graph on the right deceive you a little bit. That's not actual thicknesses of layers within the star. In a type 1 supernova, I might jumping ahead of myself here. I'm a little bit. Okay. So I'll come back to this particular graph again because it helps set some things. So type 1b and type 1c supernovas are the least common, at least compared to type of two main super categories of supernovas. They require stars whose mass is greater than 25 solar masses, so about 25 times the mass of our sun. And you might get a type 1b or type 1c supernova. You might also get a type 2. The mass is one of the main factors that helps determine that. These supernovas are typically found in star-forming regions, like, say, the Orion Nebula or the Tarantula Nebula, which are very prominent and active star-forming regions that we can see. What helps separate these two out from type 1a is that these types have taken this outer layer of hydrogen here, and their age and temperature has essentially caused this outer layer of hydrogen to be blown off into space as a preliminary development into a nebula, a planetary nebula. And that leaves behind this helium core and potentially up to iron. And this helium is just ejected off in a variety of ways through the star's own stellar winds, like our sun is constantly throwing off particles towards Earth. As part of that process, it takes some of this hydrogen with it. And different stars can have much more intense stellar winds than our sun. Another potential way is that a companion star, like, say, a nearby white dwarf or neutron star, is just stripping off this outer layer of hydrogen, which results in this causes instabilities in the stars. What separates the type 1b and the type 1c from each other is that the types 1c have also lost that outer layer of helium. So when a star progresses through its life, I should have included this earlier, it starts fusing helium, and then it'll eventually start fusing hydrogen, then progresses into helium, then fusing the helium into carbon, and all this eventually builds up into the core. And so the lighter and elements are farther and farther away from the core as the star progresses through its age, because there's just not enough pressure out here to fuse this helium into carbon as it gets farther and farther away from the core. So it essentially just sits there inert in the star. And that's where you get this point where this hydrogen and helium layers will get stripped off through various means. So the aggressiveness of the stellar winds, or in some cases, a feeding companion star, as it strips away this outer material, results in the star becoming unstable. The mass loss, it loses sufficient mass where it can no longer sustain the pressures in its core to maintain nuclear fusion of whatever heavier element it's trying to fuse at that point. Sometimes oxygen, sometimes iron, depends. And this instability will eventually result in a supernova. So, I had that. Can't see because I have some chats in the way. So, now separating that out, we get to type 1a supernovas, which are one of the more significant and important ones for astronomy. These generally occur in a binary star system where one companion is a white dwarf star, and the other star can be any other type of star, like, say, just a general dwarf like the sun, but it will usually more commonly be depicted as a giant or supergiant star orbiting around this smaller white dwarf. And the proximity of the white dwarf to its companion star results in some gravitational interactions where the white dwarf will start feasting upon its neighbor, stealing material from it. And eventually, this white dwarf will gain enough mass that it will exceed a threshold, what's known as the Chandrasekhar limit, which is a mathematical model that basically dictates how massive a white dwarf, a neutron star, can be before they become unstable and then transition into a black hole or disintegrate, in the case of a supernova here. So the white dwarf, once it reaches this limit, that star becomes unstable and results in a supernova. And in our case, the additional mass collection, the white dwarf will usually transition into a neutron star. What makes type 1a supernovas so important for professional astronomers is that this process, because the Chandrasekhar limit sets a hard limit on the size and mass of the star, it also sets a very well-defined peak brightness of a type 1a supernova, making them very useful in establishing how far away things are in the universe. So if we find a type 1a supernova, since we know what the maximum brightness can be, we can use that, work that back from certain other physical laws like Hubble's law and Leavitt's law to determine how far away that particular star was. So kind of help sort all of that down for us here. But mostly we'll come back to this other portion with the type 2s here in a moment coming up. But if you wanted to help identify a supernova just looking at its spectra, for a type 1a, it's a star that does not have helium in it. It may have silicon. If it does, it's a type 1a. If it doesn't have silicon and you can tell if it's a type 1b or a type 1c by whether or not helium is present. And if it does have hydrogen in its spectra, then that strongly suggests that it is a type 2 supernova. And we have to look at some other stats in order to determine if it's a type 2, which variation of type 2 supernovas it is. So in short, look for presence of hydrogen and helium in supernova, and you can roughly tell what type it was. From there, we can now move on to type 2 supernovas, which I think many people enjoy talking about more if they ever talk about them, mostly because of how they wind up. So these are stars that have a mass generally between 8 and 50 times the mass of our sun. Stars can get much more massive than 50 times the mass of our sun. So there are some other ways that and while those stars will usually end up as supernova as well, if they're above 50 solar masses, there are some other things that go on with that in terms of how those will die. Sometimes they'll directly collapse into a black hole, for example. So type 2s are distinguished from type 1 supernovas, as we just saw in the previous chart, by whether or not hydrogen is present when we go take a look at their spectra with a telescope. There are 4 different subclasses of type 2 supernovas, designated L, P, N, and B. We'll talk about the first 2. I can't remember if we're going to talk about the N class and the B class. But the primary way that you distinguish the subclasses of type 2 supernovas is by looking at how the luminosity of the star changes after the initial explosion. So if I take a quick peek ahead here, come on. 1 second. Oh yeah, I thought I might be up with that. I think I have a chart somewhere in here to help distinguish this a little bit better. But depending on how quickly that light decay occurs determines what its subclass is. What makes these the main sorry, what is this? So the mass of these stars because and the fact that they're supernovas is driven primarily by the fact that they're so massive that they can eventually start fusing their heavier elements into iron in their cores. Iron is chemically interesting in that when if you fuse 2 iron atoms together, it takes more energy to fuse them than the energy that fusion releases. This so this essentially serves as a hard stop on stars for their lives, because they don't the fusion of iron doesn't give them energy to help resist the gravity of the star, causing it um sorry doesn't allow the star to resist the gravity that's crushing the star into, a black hole or a neutron star. So once they get to the point where they're fusing iron, um, I'm not quite sure I wrote that first line correctly. I might have a retcon mistake there. But once the star starts fusing iron, it sets off the ticking time bomb. It can't start it it can take minutes to hours after the presence of iron forming in the core of a star before it starts triggering the supernova explosion. So once iron, so shortly after you get that first uh, formation of iron, the outer layers of the core will collapse inward. So essentially, think of it as like a giant, like a star sucking in its gut, trying. And this star will essentially, the core will collapse in on itself uh, very quickly, to the point where that material will move up to 23% of the speed of light inwards towards the star. And I wish I had a better video or something to help describe this rather than me sitting here waving my hands behind a computer where no one can see me. But uh, you can think of it as like trying to squeeze a rubber ball in. And at a certain point, that rubber ball is going to let back out. It's going to release all that energy as it got squished in. So this triggers essentially a rebound. So that core of the star is like a giant rubber ball, will shrink in, will shrink in and then expand out and force all of the lighter layers that didn't get sucked in to accelerate away from the star, which is what we end up seeing as a supernova. I'm sorry, it's a bit of a mouthful right there, and how I wanted to phrase that without being too terribly confusing. There's quite a bit there that I just drove into. Any questions? Some of this requires certain imagery, and I didn't have enough here that probably would have helped clarify some of that more. Seeing any questions? So here's the first of two graphs. So as I mentioned, there are the two types of supernova, the P type, which stands for plateau. And I was mistaken. I didn't actually go talking into the different types of type 2 supernova, mostly because as I said, they were just distinguished by their light curve. So the plateau types here have this initial bright spike where the star blows up, and then its remnant will start spreading out over time. Then for a P-type supernova, it'll maintain brightness for a certain period of time and then sharply drop off. So this is where the P for plateau comes in. And then L is just for, I think, luminous, where it just goes from a bright curve and then rapidly decays. So this is a not terribly great image that I took last year of the supernova in Messier 101, which is right down here, this bright star here near the bottom by the red arrow. This is was eventually cataloged as a type 2L supernova, so it didn't have this really bright spike followed by this rapid decay. And as you can see within this image, this star here is actually brighter than the core of M101. These other bright dots all around it are actually foreground stars that are within the Milky Way, but this here is not. So this is kind of contextualizing what you'll often see is when an astronomer says that a supernova outshines its host galaxy. From our perspective, is kind of you would think, oh, that's really bright. Really, it's just that it becomes a very bright star that within the rest of the galaxy is easily distinguishable from the, what might be the much brighter core here. So this is definitely a very bright explosion. And then lastly, finishing up with the third kind of special class of supernova, which are termed the superluminous supernovas. They are a little bit harder to distinguish. They're very similar to what for type 1c or a type 2n supernova. I don't have any I'm not going to just delve into type 2n's in this presentation, so I don't have any facts with me to help say what distinguishes it. But the superluminous supernova is generally classified as any supernova that has a luminosity 10 times or more that of an average supernova, which is a lot of light. So what this is essentially saying is if this supernova was a type 2 supernova, and if you look at all the other type 2 supernovas that we've looked at, if this supernova is 10 times brighter than the average of, of all of that, then we classify it as a superluminous. These are actually a much more recent development for astronomies. And with the first superluminous candidate was identified in 2003. And there's a couple of different theories for how these particular supernova come about. I will talk about the collapsar model and the pair instability model, mostly because I like these because they're just really cool physics. But this right here is an example of, if you recall that chart I showed earlier of the stellar evolution, this is what I mean by it. There are certain edge cases and exceptions with terms of how a star can wind up as a supernova. And the collapsar model and the pair instability model are examples of that. So the pair instability model is believed to occur in stars that have a mass of about 130 to 250 times that of the sun. What's due to what's known as the Eddington luminosity, 250 solar masses is generally considered the largest possible mass of a star. The Eddington luminosity is also used in black holes as a way of saying, if I take gas and I try to shrink it in towards the central point, it's going to want to put out heat and light as it collapses, and this puts off radiation, which pushes gas away. So it's essentially a self-regulating mechanism that controls how quickly or a star or a protostar can accumulate material, which essentially limits how quickly, I see your question, Mike. Let me finish, then I'll get to you. So it controls the limit of how quickly a star can gather material and build mass. So this prevents, a star with 1,000 times the mass of our sun, for example. Mike's question, which I didn't see until I started the slide, he asked, do I know why it wasn't until 2003 that they were first identified? I think the main thing there was better. So with the first actual supernova that we managed to study being detected in 1987, the main thing there was having enough data of supernova to look at, and having automated telescopes that's able to, in space, to help detect these supernovas. So Hubble was definitely a contributor there, but we also have other space-based telescopes and ground-based telescopes that hunt supernova, specifically looking for those sudden brightness and energy spikes from the explosion. And in order to distinguish these, we just had to have enough supernova to look at before we started saying, hey, there's this group of outliers here on this, what might be a normal bell curve with a nice central hump. And then you have representing like all the type 2 stars, or the type 2 supernovas and type 1 supernova. And then over off to the side, way out, you have this weird spike of occasionally, very bright supernovas in that. So we just didn't have enough data at that point to help separate them out. And I identify that these were actually a thing.
Okay. Yeah, I figured it was something like that. So thanks for pausing and addressing that. Appreciate it.
So circling back to the paired stability model. So the stars are just so massive that inside the cores of these stars, the fusion process is generating a lot of high energy gamma rays, which, in addition to the energy of fusion helping the star resist gravity and collapsing on itself, the gamma rays are also part of that process. So the fusion and gamma rays are just sitting there in the core, helping the star maintain stability. However, stars this massive do not live very long. Their lives are within 10 million years or less. So as this core material within the star is shifting about, this creates imbalances in how the gamma rays within the core are produced, sometimes producing more, sometimes producing less. And these gamma rays will collide with other things in the core, creating free electrons. And as photons will merge occasionally with other subatomic particles and turn back in from a photon into an electron. But in addition to electrons, they also produce antimatter positrons, which is the antimatter component of an electron. And for those familiar with antimatter, when matter and antimatter meet, they annihilate each other. This loss of, although this does produce energy, this actually, for a reason I don't quite understand, results in a pressure drop in the core. So this repeated cycle of, gamma rays produce electrons, produce positrons that then disappear from the core, eventually will cause enough of these a mass loss in the core, because it gets converted all back into energy and nothing there for it to fuse. And the star will not have enough mass to resist gravity. This causes the star to collapse in on itself and trigger the aforementioned superluminous supernova. Interestingly enough, in terms of outcomes, this does not produce a black hole or a neutron star like the type 2 supernovas and some type 1 supernovas do. The star just essentially just obliterates itself, and you just get left behind with a nebula with no other stellar remnant in it, which is cool. Just having 250 solar masses just obliterate itself with nothing left behind. And then the other way you would get a superluminous supernova is what's known as the collapsar model, which is just astronomers playing fancy with portmanteaus with words. It simply just means a collapsed star. This is like type 2 supernovas. This is another way that you can get a stellar mass black hole. But what sets them slightly apart from the normal type 2 supernova is that you need the star's core to be rotating very quickly. And not the star itself rotating very quickly, but the core. So the core and the outer layers of the star may be rotating at different rates, because you can think of the star as a fluid, but not fluid. Plasmas can behave as a fluid in some cases. But the core of the star, in addition to rotating very quickly, just the core, not the outer layers, thinking back to that onion I showed earlier for type 1 supernovas, just that inner core needs to have about 15 solar masses or more just in the core, which means that we need to be looking at a star here that fits somewhere between the 25 to 90 solar mass range, is what that core mass eventually translates into. So this core rotation actually causes jets to form within the star that we can't yet see. And those jets will then, as they try to escape out through the star's polar regions, run up into the outer layers of the star. And that somehow, that combination of just these jets hitting these outer layers blows them off the star and causes a supernova. And we get a lot of X-rays and gamma rays. So this is kind of also part of a process of which you might get a gamma ray burst. It's a bit of a hand wavy stretch there without some diagrams, which are just very hard to find to illustrate this point. And that actually wraps up the entirety of supernovas. This here was the actual chart that I thought I had much earlier, that just shows how supernovas luminosity changes over time, which is important for how we distinguish type 2 supernovas here. So this is that. So here's the where do I want to start this? Looking at this legend. So we have the type 1 luminous, the type 2 plateau, the type 2N up here, and then the type 2B. So these are the freaky one where they bright and then they fade and then they suddenly quickly brighten up all again before decaying down. And so I think the reason they explained this, which I didn't really fit well to the presentation until I added this graph late last week, is there's a material buildup as part of the supernova remnant catches up with gas that was ejected earlier. And then so there's gas that's ejected from the star prior to the star going supernova. It goes supernova, and then those outer remnants accelerate away quickly. They eventually will then collide back up with that earlier ejection material, and then trigger another wave of brightness before settling back down. I had to remember that all off just from looking at a graph number. And then these are just the other, type 1 supernova, type 1A, which is a standard candle. And then type 2 B and C have very similar curves, which is why for type 2, 1B and so for type 1B and C supernovas, spectra is more important than the light curve because they both have a similar light curve, as you can see from this graph. And that's it. Questions or comments or things I flubbered over a little bit when trying to explain? Could use more info. Not hearing any talkers or seeing anything in the chat. So sounds like I did a pretty good job then. Or I hope you guys at least got something out of it. For next month, I believe, what I have planned for next month is giving a presentation on galaxy classifications or galaxy types. And I believe Pete Hermes will also be giving an astronomer of the month. But look, keep your eyes out for the next meeting announcement for the exact topics. It may change with Pete's availability because he does engage in firefighting this time of year. And with that, I'm going to go ahead and